Oh, it's okay. You can start.
Excuse me a few seconds, please. Okay. Good morning, my dear colleagues. Today I will talk about color magnetic and color electric confinements in QCD. And I try to begin with some simple ideas. I will discuss field cumulant method. So I need to admit that the aim of this method is to find fundamental properties of the vacuum configurations which ensure confinement, and more technically to introduce a formalism which enabled one to describe long-range processes in terms of background field vacuum correlators. At the present stage, there is no proof of the proposed approach can be given. Some assumptions can be, however, qualitatively checked against experimental data and conventional wisdom. So, the most important statements of this method, first of all, we need to assume that the gluon field can be decomposed into the non-perturbative and pattern the quantum fluctuations. We assume also that both non-perturbative gauge potentials and non-perturbative field strengths are large in the QCD scales, and all physical amplitudes and green functions are obtained by averaging over background field configurations. And the last one very important property that I need to discuss that QCD vacuum correlation length is extremely small. So we are dealing with stochastic vacuum model. What's the price for that? We can obtain the area alone in this model. That is the most important property, I guess, that I will discuss today. So, let's begin to describe the field cumulant method. One of the most important properties in this method is the concept of bilocal correlator. Here in this case, the parent and symbol means Young-Mills Lagrangian averaging. In addition, in this approach, we use two Wilsonian lines, which indicates as phi xy. These lines are taken in the fundamental representation. And so the bilocal correlator can be recorded as in usable form by means of relation on this slide. As concerning bilocal correlator, we can introduce two important scalar functions, d and d1, that play a crucial role in the field correlator method and in bilocal correlated structures. It is quite clear that we can talk about an electric and color electric and magnetic color field strengths so from the latest data and also from the analysis of experiments for strong interactions, it can be concluded that the correlator between the color magnetic and color electric component turns to zero. Functions d1 and d, that is two scalar functions with indices E and H determine the QCD dynamics completely, and in particular they are associated with the tension of color electric and color magnetic strings. So we see on this slide that functions D with indices EH define all confining QCD dynamics, and so we see the relation between color electric string tension and color magnetic string tension, and functions D and D1. Note that in the case of color electric string, the plane of integration is associated with the space-time domain. It is better to say that not a space-time, but space-Euclidean time domain. But in case of color magnetic string, exclusively arises from a space-like domain. Of course, at zero temperatures, the tension of sigma E and sigma H coincide. So when we find the dependence of function d, e, h with indices e and h, it allows us to say that we have calculated the dependence of the string tension on temperatures. It is worth saying that at temperatures greater than 0, the behavior of the electric and magnetic components is completely different. While in the confinement transition domain, the electrical tension of the string undergoes a significant drop, and above a certain temperature actually turns identically to 0. At temperature significantly higher than the transition temperature, the color magnetic component grows almost quadruply. That is. As a consequence of this behavior, we see significant difference in the dependence of color magnetic and color electric condensates on temperature. To solve the problem, we need to find a connection between function d and so-called two-gluolump green function. To do this, we need to revert the expression for bilocal correlator in the following form. Here we use the fact that the integration is carried out along the straight line that is connected point x and y. Thus, we get the following expression that is on, we see it on this slide. And finally, the bilocal correlator can be expressed through the field strengths in the algebraic representation as well as the Wilson line in the algebraic representation. And the next step, we will connect such a bilocal correlator with the gluelump green function. Excuse me. So we decompose field strengths of the corollary electric and magnetic field into the abelian and non-abelian parts. Then bilocal correlator itself can be represented as the sum of three terms, D0, D1, and D2. Here, in each term, the indices denotes the degree minus 2 by the degree of the coupling constant. For example, for D0, that is, for D0, we get an expression that associates it with one gluelump green function. The same expression includes also delta 0, which denotes the contributions of higher order cumulants that we have the right to completely disregard. One gluelump green function itself can be written in the following form. This is the last equation on this slide. So we need to understand what does that mean from the physical point of view. The fact is that this formula can be interpreted as a movement of the gluon from point X to point Y in the field of stochastic adjoint source. That is gluon at point Y. So on the left side there is a gluon on point X, and there is a adjoint source, the static source that give us a color field. So as a result of averaging, we obtain the formation of string between the gluon and surface. And all we have to do is to take into account the Casimir scaling hypothesis. So in such consideration will allow us to obtain the expression analytically if it's necessary. Here on the slide, we see a visual picture that illustrates the procedure described above. It is worth noting that such an assumption allowed Yuri Antonovich Simonov calculate the mass of one gluelump state. With such an example in mind, we now turn to the simple D with two indices. That is, we see it on this slide. It is that allow us to calculate the tension of the string, both in electric and magnetic case. So we see that D2 is expressed in terms of gauge potentials of non-abelian fields as follows. This equation on the slide. And by analogy with the example discussed above, we can say that in this case, we need to talk about the movement of two gluons in the field of the adjoint source, which interact with each other and simultaneously interact with the static adjoint source. The averaging procedure will lead to the formation of the fundamental strings between the system elements. This is exactly the situation depicted on this slide that you see in front of your screen. It is worth mentioning right away that when I said phrase static source, anyway, I meant that it naturally moves along the imaginary time, which corresponds to the axis in this figure. We see two-gluon trajectories, the time slice, and marked in gray that are marked in gray, and the strings are marked in black in this figure. In fact, our task is to be able to calculate the integral along the trajectories for the figure. So we know that here it is well described. Feynman-Fock-Schwinger formalism comes from to our rescue, which allows us to represent the green function of two gluelumps in the form presented on the slide. Here the parameter S and S bar refer to the proper time of the first and second gluons. Wilson loop WC bars Z bar Z is averaged over the gluon fields along the path Z, and Z bar in the field of static adjoint source with a spatial coordinate that moves along that axis entirely. This procedure leads to formation of the strings between gluons themselves and gluons and the source. An extremely important circumstance for us is that the integral of the first component is taken along the torus and is responsible for taking into account the contribution of finite temperatures. We specifically added the W indices here. Therefore, in the case of magnetic string, we may say that the integral along the torus is actually divided into the spatial part and the part that is responsible for the final temperatures contribution. As for the torus integral, it can be computed explicitly and shown in the slide, and this means that the fact that we must calculate the integral from the remaining part of the action provided the weight factor arises. I guess we can rewrite it in the form that you can see on the slide. As for the Wilson lines, it is also divided into temporal and spatial parts. Temporal, I mean the imaginary time direction. In imaginary time direction, we will go away from the proper time and go to the parameters that I will call omega 1 and omega 2. Thus, we will come to the formula that depicted on the next slide. It is worth noting that the values K, E, zeta mean the following expression, and thus, as for interaction potential between gluons and adjoint source, we can use approximate formula that depicted on this slide. Here, sigma F means a string tension in the fundamental representation. So we have at this moment we have all the ingredients to obtain the spatial string tension as a function of the temperatures. So on the next slide, we see a very complicated formula that describes the final answers that we obtained after very difficult calculations. It is also worth saying that the M on this slide parameter means which depends on omega 1 and omega 2 is called the gluelump mass. Moreover, we see that the string tension depends on the running coupling constant, which is given on the temperature scale. Within the framework of this approach, or approach of the field correlator method, such a run arises very simply due to taking into account perturbative modes. Nevertheless, it is immediately worth noting that the running coupling constant starting from a certain scale freezes in FKM method. As you can see, the expression is very complicated and is very complex, and direct calculation seems to be a technically very difficult task. However, we can test our logic based on the following assumptions. The fact is that the structure of this formula for the spatial string tension implies that we may assume the averaging over by temperature and integrating over by omega and omega-2 reduces to the occurrence of some additional average value, which we indicated by delta W average on this slide. We want to compare our theoretical calculations with latest data and show that such parameter exists. Moreover, we hope that it will not differ much from one. Let's put all thoughts together. First of all, let's look at changes in the coupling constant with scale. As we can see, this leads to small logarithmic corrections. This is a figure of behavior of ratio of the running coupling constant to the constants on critical temperature scale. I also would like to say that all our calculations we made it in gluodynamics, not in QCD. So after that, we carry out main test of our work. As we can see from our positions, there really is such parameter, omega average, that is able to fit all of the latest data from the transition temperature in gluodynamics to very high temperatures. You can see it on this slide. I also want to point out that latest measurement errors also is plotted on this figure. This is small black lines on this figure, that is errors of latest calculations. The most interesting thing is that the omega average parameters that we obtained, as well as taking into account running of the coupling constant, only slightly reduces the growth of the color magnetic tension of the string with temperature. Some intermediate conclusions in which we can say we have calculated the color magnetic string tension. Color magnetic string tension at different temperatures. So in practically, that does mean that the change in string tension is a range of T and from 0 to critical temperature. That doesn't change significantly. This is spatial string tension or color magnetic string tension doesn't change significantly from the this 0 temperature to the critical temperature, and after that it begins to grow significantly. That also means that we have made sure that gluodynamics like QCD at temperatures above the transition temperature are still non-perturbative theory, and this fact is very important both for describing dynamics and thermodynamics. In our method, that is also manifested in the that there exists fundamental scale at this non-perturbative scale at this temperature that will completely will be compete with the temperature, and that also means that for example, leads to the fact that the QCD or gluodynamics, even for very high temperatures, the Boltzmann law will not be reproduced. Despite this, we can also notice that we are undergoing spatial reduction. That means the dimensional reduction. As you probably remember, at very high temperatures, gauge series are static. This is actually similar to the statement that zero Matsubara frequency makes dominant contribution to all basic quantities. In our method, the spatial reduction temperature is approximately 1.3 critical temperature. Here, an attentive listener will immediately be able to wonder how it turns out that the tension of the color magnetic string is growing. Moreover, the color magnetic condensate is growing. And does this mean that the growth is not fundamentally limited, and the gluodynamics at attaining temperatures is always non-perturbative? The answer is in the structure of the expression itself for string tension, for color magnetic string tension. The fact is that we have a running coupling constant that gradually reduces the tension of the string, and the square root of it behaves not as a temperature, but as a temperature which is divided by the logarithmic corrections. The second point is related to the fact that we assumed that the mass of the lowest gluelump itself does not depend on temperature. And it is much greater than order of magnitude of critical temperature. In fact, this assumption is justified, as we can know that the region of Tc over m of gluelump can be characterized by a value of order of 10%. As we see, at a temperature comparable with the mass of the lattice gluelump, we will have to make some significant changes in our methods. So, the next part of our talk, will be related to work of Yuri Antonovich Simonov and his co-author Mikhail Lukashov. It will be devoted to the color electric tension of the string. I will tell you briefly about the main statements that Yuri Antonovich and Mikhail have received in their work. Any questions? As you understand, okay, maybe if you would like, I can give an answer. I will see a hand that on my screen. I can give an answer to your question. Or later.
May I ask?
Okay.
Asking. In the beginning of your presentation, you mentioned the long-range processes. Which processes did you mean?
Long-range processes, I mean that non-perturbate, there are some scales in my theory. First of all, it is temperature. The second one is associated with the string tension. That means that I try to discuss physics on very long scales. For example, that is compatible with hadron scales and maybe bigger.
Did you mean the hadron scattering, for example?
Not at all. Of course, my methods or field cumulant methods could also describe such a physics. But at this point, I'll rather will I prefer to talk that this scale is somehow I can give an amplitude. It will be some kind of one graph about of these processes. I mean. So the critical temperature in the case of gluodynamics, it is 270 MeV. And for example, the lowest gluelump mass is 1.6 GeV. So I try to talk about such energy scales. Okay?
Yes, thank you very much. I believe that during the discussion session, maybe we'll discuss other things in more detail. Thank you very much.
Okay, so thanks a lot. So the next part of my report will be related to work of Simonov, Yuri Antonovich, and his co-author Mikhail Lukashov. And as I say, it will be devoted to the color electric tension of the string. I will tell briefly about the main statements of his works. As you understand, the problem of calculating the behavior of color electric tension of the string in the vicinity of the beginning of the fast transition is one of the fundamental questions of QCD. Of course, we know very well that in QCD with 3 colors, this transition is fast transition is a crossover. So in this task, this task is one of the most important forms from the point of view of this kind of the QCD. The authors propose to connect the behavior of the color electric condensate with the behavior of color electric string tension. They proceed from the following provisions. They suggested that the free energy of the system could be represented as the contribution of color electric condensate plus hadron pressure. So one must define the behavior of the vacuum energy. Here it is F1 or T as a function of the temperature, which will explain the properties of the hadron gas and its deconfinement transition. And they try to impose the following condition on the free energy, which they called the vacuum dominance mechanism, where the hadronic pressure is growing with the temperature T, the simultaneous decrease of the vacuum energy of the gluon condensate, so that the sum is kept constant. So they just impose the following condition. And after that, in case of field cumulant method, the behavior of quark and gluon pressure is well known. They prefer not to use hadronic pressure. They prefer to use quark and gluon pressure. On this, you can see this condition on this slide. And after that, they try to resolve the equation that you can see on this slide. From these equations and from these conditions, they try to find the critical temperature, and after that, they try to connect, for example, the color electric condensate with the string tension, and try to make some predictions in case of lattice simulations and in case of real QCD experiments. And they try to find the answer to the following questions. The first one is connected with what is the deconfinement temperature, let's say, of the vanishing string tension for different thermodynamic systems. They try to change the number of colors. They try to change number of fermions. After that, they try to understand how the color electric string tension decreases with the temperature, and moreover, why it is decreased so far before vanishing at T that is equal to critical temperature. The third question is why the color electric string tension depends strongly on the contents of the thermodynamic ensemble, so that why, for example, the critical temperature for pure gluodynamics is equal to nearly 1.5 critical temperature of QCD with two critical two fermions. And the last one is what is the connection between the color condensate and the string tensions and how it is connected with the lattice data. I also would like to mention that they made another additional assumption. They also know, they understand quite well that the quark condensate term that must be equal on the slide, this is literal epsilon with index Q contribution around 10 or 15% of the total vacuum energy, and disappears at the same temperature they clearly understand that it is not vanished, almost vanished, but they neglected it at the first approximation. So they try, as you can see, if we have color electric string tension, and for example, color electric condensates, we can use the following identity, and we have a relation between the color electric condensate and the color electric string tension that you can see on On this slide, at this point, one takes into account that color-electric string tension can be connected only by color, only by the color of excuse me, can be connected only by to the color-electric part of gluonic condensate. So we obtain such a simple equations that you can see on this slide that the string tension directly connected to directly could be calculated as a square root of color electric condensate that in turn is could be calculated on the lattice. They prefer normalization condition at the temperature that is equal to 0, so one can obtain an approximate formula that sigma color-electric sigma is equal to 5.4 square root over gluonic condensate. They also, I would like to point out that they prefer to neglect the dependence, temperature dependence of the alpha. So in this way, we have connected the gluonic condensate G2T with the string tension sigma sigma electrical T, and in what follows, we shall be able to deduce the decrease of sigma T for 10 approximately, that is equal approximately to TC using the corresponding decrease of the G2 T connected to the basic equations of the hadronic medium. One can obtain the following connection of the gluon condensate with the pressure of hadronic phase, and thus we can calculate its color electric string tension not only in for example quark gluon plasma, but also in hadronic media. So as you can see, we can obtain the for color electric string tension very simple equation. This is the first equation of this slide. And after that, one can use an approximate formula for hadronic string tension, PHT, that is equal to temperature in the fourth power over some additional factor. And so we can obtain very simple laws. That is the second equation on this picture. And one can see that the fast growth of the hadronic pressure near critical temperature in this equation makes the transition curve of sigma color electric string tensions very steep for both light and heavy hadrons. So with now time we try to test this equation and try to compare this with the latest data. So on this figure you can see the comparison of the latest data for the ratio of color electric string tension over color electric string tension at zero temperature. They try to compare it with the data of the lattice group that of the two lattice group that is depicted on this figure. And as we can see, there is quite reasonable agreement between the prediction, I mean, between predictions of Mikhail Lukashov and Yuri Antonovich Simonov and the latest data of group of Busida at Caucasus and the latest group from the work of that is depicted on the slide. They also made a very interesting predictions for temperature dependence of color electric string tensions with respect to hadron mass. So as you can see on this slide, they observed that the ratio sigma over sigma null for different values of the hadron mass, for example, mass of pion, mass of romizon, as mass of gypsy, that is dashed lines, and they find that with growing of the mass of the particle, the string tension tends to lower with tends to increase speed of the lowering of the spatial of the color string tension. That is, you can see on this slide. So, and after
Yeah,
that,
5 minutes.
5 minutes, quite well. And the last, maybe not the last, but almost for my final expression, they try to use dimensional arguments, so they understand that the ratio between condensates, quark condensates at different temperatures is equal to 3/2 power of the ratio of colors electrical string tension sigma at temperature scale T over sigma at 0 temperature scale. So they obtained this law that you can see on this slide, and so they try to compare these predictions with the latest data, and so observed a very interesting result that, for example, the behavior of the quark condensate is a function of the temperature, and their predictions with such a simple formula behaves quite well in the from in temperature domain from, for example, 0 temperature to nearly temperature of the beginning of fast transition. That I guess that's almost all that I want to say. As for critical temperature, they obtained also some predictions, and the main idea that I try to talk about, that the main assumption that there is some relation between gluonic condensate and the spatial string tension, I mean color electric string tension, works quite well from the point of view of understanding of the latest data. That's all, I guess, that I need to say about their predictions, etc. So I think that it is better, of course, to see their work and to try to understand their calculations. But I guess I say everything that I think that I need to say about this work. So if you have any questions, I guess I try to answer to them. And so thank you for your attention.
Okay. Thank you very much for a nice presentation. Please, questions first from Zoom.
Okay, excuse me. May I ask the question? Andrei Katay
Yes.
speaking.
Yes, of course.
Yes, I'll try to open the. Not sure. Okay. Thank you for a very interesting talk. The question is the following. You demonstrated that for the temperature, when you're including the temperature, both quark condensate and gluon condensate are changing.
Well,
okay, fine. Then there is the well-known PCA relation between mass of pion and the product of masses of light quarks and quark condensate. From your considerations, I saw that the masses for the temperatures considered, the masses of U and D quarks are 0. Then you have temperature dependence of C bar Psi, and on the right-hand side, due to the well-known PCA relation F PMP times square, there should be equality. Whether this equality is true, or what is happening with pion mass, or maybe F pi is I don't know. May I ask this question?
Okay, that's quite well question, because of course there's the relation between pion mass and masses of the largest quarks, for example, up and down quark. But as I talked, or maybe as you can see from the work of Misha Lukashov and Yuri Antonovich Simonov, they, instead of really zero quark mass, they prefer to use very low but finite quark masses. As you can see on the table, they use, for example, the mass of up and down quarks that is equal to 3 and 5. I need to say that field cumulant method behaves not very well in case of zero quark masses. Just because it is very important, for example, that
I see, and
it's a very
that's
important property that they I try to remember, but it is Ginsburg-Wilson relation or something like that. I mean, this is very famous formula, but a few seconds I try to formulate the correct answer. And so in case of zero temperature, that means in case of the zero quark masses, they must obtain zero pion mass. That's whether I correct understand the question or not.
okay. Oh, okay. Yes, I see. There is the comparability. If you are taking the zero quark masses, then you are obtaining zero pion mass.
Exactly.
Course,
this is
and
Goldstone
so,
theorem, right?
everything from this
Goldstone, yes,
point of view, everything is consistent because okay, and it is multiplied zero quark masses. The sum of zero quark masses is multiplied by some temperature dependent non-zero quark condensate. Okay, thank you.
Okay, thank you very much. More questions from Zoom? No, maybe from audience, please.
Zakhar, thanks a lot for nice talk.
Mm-hmm.
I have many questions, but I formulate only one. You made a statement that spatial string tension at very high temperature goes to 0. On the other hand, another statement was that we have dimensional reduction, so the four-dimensional theory goes to three-dimensional one at high temperature, and in three-dimensional theory we have confinement for all couplings. So it looks like contradicting statements.
Not at all. I try to reformulate these statements. First of all, I do not say that the color string, spatial string is breaking. Just because I only mentioned that we have some arguments that this such as spatial string could break at extremely high temperatures. Indeed, at temperatures that is equal to, for example, to critical temperature or 5 critical temperatures, we observed that the spatial string tension is growing. In any case, if you can see, for example, if you look at this slide on your screen, you can see that there is two factors: F that depends on the omega-1 and temperature, and F that depends on omega-2 and temperature. And this, when I talk about dimension reduction, I meant that these factors is equal to 1. At fine, that means that it, for example, at temperatures that is lower than, for example, 1.3 of critical temperature, with these factors doesn't equal 1. So they a little bit lower. So they are sensitive to the temperature dependence. In case when you are try to calculate some quantities at temperatures higher than the, for example, 1 and the 3 temperature critical temperature, this factor is equal to 1, and from this point of view, we obtain the dimensional reduction.
Okay, If no questions, let us thank the speaker again, and I invite the next speaker, Vitaly Barnikov, please.